Good morning. In the session number 5 of design of compression members, I'll be explaining you the design of axially loaded circular columns. So before going to the design of axially loaded circular columns, some of the governing equations of axially loaded circular columns with helical ties are: the columns with helical ties generally takes more load than that of tied columns. That is, the circular columns with helical tie has got more load carrying capacity than with the rectangular column, which are tied by the rectangular ties. Due to the additional strength of the spiral contributing to the strength of the columns accordingly. As per clause 39.4 of IS 456 recommends a multiplying factor of 1.05 regarding the strength of such columns. The code further recommends that the ratio of volume of helical reinforcement to the volume of core shall not be less than 0.36 in order to apply for the additional strength factor of 1.05. Accordingly, the governing equation as explained in the design of axially loaded rectangular columns, that is PU equals to 0.4 FCK into AC plus 0.67 FY into ASC. This particular equation will be multiplied by a factor of 1.05 when it comes to the design of axially loaded spiral loaded circular columns with helical ties. Earlier observation of several investigations revealed that the effect of containing hold good in the elastic stage only, and it get lost when spiral reaches the yield point. So the spiral reinforcement, which helps in increasing the strength of the column, will be valid only at the till the elastic range, and when the column reaches or when the spiral reaches its yield point, this particular statement will not be valid. Hence, in the design of axially loaded circular columns, the effect of helical reinforcement at the elastic stage will be considered. And the spiral becomes fully effective after spalling of the concrete cover over the spiral due to excessive deformation. Hence, the above 2 points should be considered in the design of columns with helical reinforcement. Okay. The first point is regarding the enhanced load carrying capacity taken into account, that is the factor of 1.05. The second point is maintaining the specified ratio of volume of helical reinforcement to the volume of core as specified in clause 39.4.1 of IS 456. In order to effectively increase the load carrying capacity of the helical reinforced columns, the helical reinforcement need to be, the strength of the helical reinforcement need to be considered at the elastic stage. The helical reinforcement becomes more effective after the spalling of the concrete cover due to the excessive deformation. Because of these two particular points, the load carrying capacity of the axially loaded circular column will be more That is, the factor of 1.05 will be multiplied to the Gowning equation that we will be using for the particular design. So, in this particular design, determining the pitch of helical reinforcement plays a very important role. So volume of helical reinforcement and volume of core need to be identified or need to be calculated in order to find out the specified ratio is within the codal norms or not. Based on that, the pitch can be. In the design of axially loaded circular column, I'll be demonstrating a design example. In this particular problem, we have got a circular column of 400 millimeter diameter with helical reinforcement subjected to an axial load of 1500 kilonewton under service and live load. The column has an unsupported length of 3 meters. And the support conditions of the column is effectively held in position at both the ends but not restrained against rotation. And the concrete grade used in this problem is M25 and the grade of steel used is Fe415. As told in the previous session, the step one of all the design of columns is to check whether the column is short column or a long column. With the given data of unsupported length of 3 meters and with the diameter of 400 mm and the support conditions from the table 28 of Annexure E of IS 456, the effective length is equal to the unsupported length as the support condition is effectively held in position at both the ends but not restrained against rotation. Therefore, L effective by D is 7.5, which is less than 12. Hence, the column is a short column. So here, the effective length factor mainly depends upon the annexure E, the table 8, which gives you the different support conditions of the column. Based on that particular conditions, we need to consider the effective length factor, multiply the effective length factor to the unsupported length. So here, the effective length factor for the given support condition, that is effectively held in position at both ends but not restrained against rotation, is 1. Hence, L effective is equal to the unsupported length of the column. The load carrying capacity of the column mainly depends upon its support condition. And based on this support condition, the effective length, the length which helps in resisting the load or the length which need to be considered for the design of the column plays a very vital role. And in step 2, we calculate the minimum eccentricity, which should be either greater of L by 500 plus D by 30 or 20 mm. In this particular case, I'm getting E minimum as 20 mm. And as explained in the previous problem, the minimum eccentricity should not be greater than 0.05 times of D. In this particular problem, 0.05 times of D leads to 20 mm. As per the clause given in clause 39.3 of IS 456, E minimum should not be greater than 0.05 times of D to employ the equation given in that clause. Here, in this particular problem, both the eccentricities are same, so we can use the equation given in IS 456. As explained to you in the earlier, that the PU equation is multiplied with a factor of 1.05 because of the effect of helical reinforcement, which introduces higher strength to the column. So 1.05 times of 0.4 FCK AC plus 0.6 FY ASC. So the AC is the AC area of concrete is rewritten as gross area minus area of steel. So gross area, since I know the dia of my column, that is 400 mm, the gross area is pi d square by 4, which leads to this particular value minus ASC. Substituting PU, which is 1500 kilonewton, FCK, which is 25 Newton per millimeter square, and AG, which is pi d square by 4, and Fy in the above equation gives me an area of steel of 3304.3 millimeter square. For this particular area required, we provide 11 number of 20 mm diameter bars, which gives 3455 millimeter square as longitudinal reinforcement, whose percentage of steel is 2.75%, which is again in between 0.8 to 4% as per the codal recommendation. Hence, the provided steel